going to start immediately with an invited speaker, Özlem Salehi from Poland. What is the Institute of Informatics? I forgot to look it up. Okay, and I'm really happy to be in this this session where Özlem is the speaker. I really appreciate her work, and I think we're going to have a very nice talk from her. So please, Özlem, the floor is yours.
Thank you for the presentation and thank you for the invitation. This is Özlem, and today I'm going to present you our work titled Near Optimal Circuit Design for Variational Quantum Optimization. This is joint work by Bakó, Glos, and Zimborás. So let's start. Okay. So here's a brief outline of my talk. I will first talk about quantum approximate optimization algorithm, QAOA in short, which is a popular quantum optimization algorithm for NISQ era quantum computers for solving combinatorial optimization problems. I will talk about the state-of-the-art implementation for QAOA. And then I will present our newer approach called Functional QAOA and how it brings some advantages over the current state of the art. And I will demonstrate this for traveling salesman problem. And finally, we will conclude. So let's start with QAOA. But to understand this algorithm, we should first understand what adiabatic quantum computing is. So let's first go to adiabatic quantum computing. You may be used to gate-based quantum computing where you apply some gates, you have a circuit, you apply C0, X, etc. But this adiabatic quantum computing is a different framework. Here, this is not gate-based, but it's an analog computing framework, and this relies on quantum adiabatic theorem, which states the following. So you have a time-dependent Hamiltonian, meaning that this Hamiltonian is changing by time. So this is h of t. And the system is initialized so that it starts in the ground state of this Hamiltonian. And if you check at time equals 0, we have only H mix acting on the system. So you initialize your system in the ground state of H mix. And this H mix is chosen so that its ground state is known and easy to prepare. Then quantum adiabatic theorem states that the system will remain in the ground state if it is evolved sufficiently slow. And what does this mean? At time equals tau, you see that we have only Hc acting on the system. And it is expected that the system ends up in the ground state of Hc. Now, how can you use this for computation? Suppose that Hc is some Hamiltonian whose ground state is not known. Then using the scheme, you can obtain the ground state of Hc. And how this is used in optimization, for instance, quantum annealing also relies on this. You design Hc so that its ground state corresponds to the optimal solution of your problem. But we will see this later on. Now, if we go back to QAOA, first of all, this is gate-based. Here you see on the right-hand side a circuit representation for QAOA. And this algorithm approximates the ground state of some given diagonal Hamiltonian corresponding to some combinatorial optimization problem. Then what is the relation to adiabatic quantum computing? This can be viewed as a triotorization of AQC. Remember, we had H mix and Hc in adiabatic quantum computing. And here we have alternating layers of H mix and Hc. And you can check this green rectangle. Inside this green rectangle, we have an operator corresponding to Hc. And those X gates, parameters X gates, they correspond to H mix. And we have P layer of them. And this corresponds to this quantum state here. We start in equal superposition of like plus states. Then we apply alternatively H mix Hc, H mix Hc, and so on. And those gates are parameterized by gamma and beta. Those are called variational parameters. And those are optimized classically, resulting in a hybrid algorithm. So this is a hybrid algorithm where we have both quantum and classical components. And there are two P parameters required for P layers. And so you construct this quantum circuit, you make a measurement, and then the classical optimization procedure gives you the parameters so that this expectation value here is maximized. So you try to maximize this HC. And actually those variational parameters, they determine how long each Hamiltonian is applied on the system. And typically the initial state is chosen as this plus equals superposition state. And this HC is expressed as an Ising Hamiltonian, a diagonal Hamiltonian. And H-mix, for H-mix, this minus Xi is chosen. Why? Because like its ground state is this equal superposition state, which is really easy to prepare. So this is the conventional QAOA. So as you can see here, H-mix is fixed, initial state is fixed, but what you need to come up with this HC and implement this HC part. So this is also called the phase operator. So this is the mixing operator and this is the phase operator. There is a generalization of QAOA called quantum alternating operator ansatz. And here you can start in an arbitrary initial state, which is usually taken to be a subspace of the full Hilbert space consisting of feasible states. And in this case, for the mixer, an operator is chosen so that it preserves the space. Let me give you an example. Instead of starting in equal superposition, you can start in double state. I am omitting the normalization factor here. You can start in the following state. Maybe this is feasible for your problem. You don't already want states like 1, 1, 1. And then for the mixer, you choose XY mixer, which is denoted as follows. And this transfers amplitudes only between one-hot states. And ordinary QAOA or conventional QAOA can be seen as a special case of this. But again, like mixer is kind of fixed initial state as well. But like then how we implement this middle part, this HC. Now, this is what I will discuss next, how we solve a problem using QAOA. So what is the state-of-the-art approach? So first, let's talk about quadratic unconstrained binary optimization. It is just an optimization problem stated as follows. You have so this is an example. X1 and X2, they are binary variables. They are either 0 or 1. And you would like to find X1 and X2 so that this f of X1, X2 is minimized. And this f, it consists of at most quadratic terms like X1, X2. You cannot have X1, X2, X3, for instance. And in general, this problem is NP hard. And one can express this also as follows in a more general form. And for this simple example, the solution will be X1 equals 0 and X2 equals 0. This is unconstrained, meaning that there are no constraints imposed on this minimization problem, but often for combinatorial optimization problem, you have some constraints. So how does a constraint problem look like? So you should minimize a function subject to some constraint like X1 plus X2 should be greater than or equal to 1. And in such a case, the optimal solution will change because this is not a valid solution anymore. It is not satisfying the constraint. But what you do in such a case, if you would like to obtain a QUBO formulation, there is a method called penalty methods, where you incorporate your constraint into your objective function as penalties. First of all, this is an inequality, and we first convert this into an equality by writing X1 plus X2 plus Y equals 1. And then this term, if you check this, this will result in a positive value if this constraint is not satisfied. And if it is satisfied, say x1 plus x2 equals 1, then y can be set to 0, and this will result in 0. So it is not adding any penalty. But whenever it is violated, there will be a penalty. And remember, we would like to minimize this. So this is the way how we deal with constraints. And once you have a QUBO formulation, or indeed you can also have a QUBO formulation, meaning higher order. It does not have to be only quadratic, but you can have like x1, x2, x3. But QUBO is more popular. So you first create a QUBO formulation for your problem. Then you get the corresponding Ising model, which you can do by this transformation, by replacing xi with 1 minus si over 2. Here, si's are spin variables. They're either minus 1 or 1. And once you get the corresponding Ising model, then you implement this term-wise. I will show this next. In general, the quantum optimization framework can be seen like this. You have an objective function, and you have some constraint functions, which evaluate to 0 if and only if the corresponding constraint is satisfied. And this should have polynomial number of terms, because otherwise the resulting circuit will have also, so if this is, say, exponentially many terms, then the resulting circuit will also have exponentially many gates, so it will not be efficient to implement. Now I will give you a concrete example. Maybe some of you know about max-cut problem. You are given a graph. In this example, we have a graph with 4 nodes, where nodes are labeled 0, 1, 2, 3. And the goal is to divide the node set into 2, so that the number of edges crossing between the 2 sets is maximized. It's not really important right now. This is just to demonstrate you how one implements QUBO. For this problem, this is the corresponding QUBO formulation. Here, each variable xi represents one of the nodes. It can be 0 or 1. If at the end of this optimization procedure, say x3 is 1 and x2 is 0, this means node 3 is in group 1 and node 2 is in group 0. Remember, we were to separate those nodes into 2 groups. But anyways, so you start with some QUBO so that its minimum will give you the optimal solution. It may not be clear right now why this QUBO is giving you the optimal solution, but that's not important here. Then you obtain the equivalent Ising model. Constants are not important. You can omit those. So you end up with this. Then you replace each spin variable with zi's and zj's, z operators. And then you implement the corresponding gates to your quantum circuit. Here we have a summation over all possible edges. There are 4 edges, so there will be like 4 terms. Z0, Z3, Z3, Z2, Z2, Z1, and Z1, Z0. And those are the corresponding gates. So this is for X01. So this is Z0, Z1. This is how you implement. You have a C node, you have this RZ gate, parameterized, and you have C node again. And this is for 03, for instance. So this is the current state of the art implementation for QAA in general. What are some drawbacks? Suppose that you have this QUBO, a higher order problem. It has only a single term. It's the product of x1 up to xn, a single term only. But if you convert this into an Ising model, where you have spin variables, then this results in exponentially many terms, and eventually exponentially many gates. So the thing is, this transformation may result in excessive number of gates than you need. Actually, there is a really simple way to implement this, not through the state-of-the-art approach. And it is always not straightforward to design QUBO. For instance, like how you go from max-cut to this QUBO representation I just showed you. And there are even more, really more complicated problems. So this is another issue. And also, you increase your sort space when you have inequality constraints. Why? Because first you need to convert them into equalities by introducing additional variables, and those variables also need to be optimized, so they become part of your optimization problem. And we introduce in this work a new idea to implement this phase operator, and we call this approach Functional QAOA. And in this approach, we don't start with QUBO formulation. We don't need the Ising model at all. And we claim that this new approach allows you to get optimal circuit designs for some problems like TSP. Now I will first go through what Functional QAOA is, and I will demonstrate this over TSP problem, traveling salesman problem. So the first step is you need to have a problem description. What are your variables? What is your objective value? And what are your constraints? Let's take TSP. In traveling salesman problem, the aim is to find, so you are given a graph. The aim is to find the closed route that passes through all nodes exactly once, and you would like to find the shortest one. So the objective is finding the shortest closed route, and the constraints are the following. All cities should be visited exactly once, and at any given time, you can visit exactly one city. So this really makes sense. And for variables, so for the simple demonstration right now, I will use those variables, but later on, we will see another representation. So let me explain this truly. Here, we will use something we call one-hot encoding. We have binary variables of the form BTIs, and this is equal to 1 if node I is visited at step t in the tree. Say we have 3 cities, then we will have variables like this, B00, B01, B02, etc. And if, say, B00 is 1, this means at time equals 0, we are in city 0. And at time equals, for instance, if you check here, at time equals 1, we are in city 2, B12 is equal to 1. And at time equals 2, we are in city 1 because B21 is equal to 1. And here, if you read this, like 100, 001, and 010, so this is called one-hot encoding. Why? Because exactly one of those bits is set to 1. And on the right-hand side, you also see another representation. There is also binary encoding, which we will come back later on, but I want to talk about it now. And in binary encoding, you represent by BT the city visited at time t. For instance, in case of, again, 3 cities, we will represent B0 by 10. So at time 0, city 2 is visited. This means for B0, I need 2 bits. Like for each time point, I need 2 bits. And this will be set to 1, and this will be set to 0, and I will read this as 10. So this is city 2, and this is city 0, and this is city 1 because this is 0, 1. And this is binary encoding. And as you can see, this is more concise because in one-hot encoding, we need n squared qubits or bits to represent the problem. But here you need only n log n, and for each time point, and then log n comes from you need log n bits to represent n cities. And okay, if we come back, once you have your problem description, then for the objective value and each one of the constraints, you design a classical program that implements the corresponding functions. And this function should return 0 if the constraint is satisfied. Let me give you an example. Say your constraint is single city is visited at time t. Then to check if this constraint is satisfied, we can design a classical program like this. And in this classical program, let's check what we are doing. Say we are given n bits from, say, t is fixed, and we are given bt0 up to btm minus 1. And to check if single city is visited at time t, we should check if this is forming a one-hot vector, if exactly one of the bits is set to 1. And what you can do to check this, we can take the summation of all those bits. And if this summation is not equal to 1, we set a flag variable to 1. Otherwise, flag is initialized to 0, and we return this flag. So if the summation is 1, we will return 0, and otherwise we will return 1. Actually, instead of 1, you could return anything else. So this is our program. And we do this for each constraint and objective value. And next, we implement this classical program as a quantum circuit. So here you see the corresponding program. So this is kind of a high-level program, high-level quantum circuit. We are not going into details of those plus ones and if not equals to 1. But all can be done using quantum gates. Actually, also classical gates in a reversible manner. So I check if this is equal to 1, and if this is so, I increment the sum here. I do this for all bits. And if the summation is not equal to 1, I set flag to 1. And then comes this RZ rotation. Remember, the rotation we also had in this phase operator. We need to apply some penalty if this constraint is not satisfied. And this is how we do this here. If this flag is set to 1, then this will perform some rotation parameterized by theta. And this is the parameter of QAOA. And then we need uncomputation to revert back what we have computed. This is really similar to Grover search, a Grover oracle, because also in Grover oracle, you set some output bit to 1 to check if some solution is like feasible or not. And then you implement some Z gates to mark the state. Here instead, again, like it's really similar idea, but we have rotation Z. And so you may wonder how we will perform this in general, how to implement those quantum circuits from the classical program. Most of the time, those operations are like arithmetic or conditional operations, which are already known how to implement, like addition, quantum addition, or quantum subtraction. Another method will be to implement a classical reversible circuit. And also, one could design, so there are some high-level languages developed for designing oracles. One could also use such to design such circuits. And then final step is to combine this with an appropriate input and mixer state. And this is Functional QAOA. Now, what are some advantages? You don't need this QUBO representation or Ising model representation at all. It's just enough to have efficient implementable objective and constraint functions. And this also expands the pool of constraint functions. Why? Because there are some constraint functions which are not efficiently implementable by the current state of the art method, but they are indeed efficiently implementable using this approach. And also it's possible to optimize some parts of the circuit. And this results in reduced number of gates. This is not possible when you implement it term-wise. There is a potential to reduce the circuit space in case of inequality constraints, as we have discussed. And also, this is easier to design and implement than the state-of-the-art approach because you don't need this QUBO representation and Ising model at all. Now, in the next part of my talk, I will show you how, using this Functional QAOA approach, one can design a QAOA which is near optimal according to different cost measures like number of qubits, number of gates, etc. This will be different than the one we discussed here using one-hot representation. This will be a new one, but again, it will employ Functional QAOA approach. But first, we need to understand what we have for state-of-the-art for TSP. So let's start with QUBO formulation for TSP. Again, this is using one-hot encoding for variables, and you need to express your constraints as mathematical expressions. For instance, for each fixed t, you need that the summation of bti's is equal to 1. And also for fixed I, you need summation over t is equal to 1 to enforce those constraints. And this is your objective function. So check that when both bti and bt plus 1j, if they're both equal to 1, this means at time t we are in city I, and at time t plus 1 we are in city j. So we incorporate the cost wij into our objective. And this is the QUBO formulation for TSP. You see we have here again penalty method, so that if this constraint is violated, we have an additional penalty in the objective function. And starting from this QUBO formulation, we can obtain 3 different QAOAs, XQAOA, XY, and GM. I will explain each. You can see that they are different in terms of the initial state and mixer they are using. And also we have a higher order binary optimization version where we use binary encoding. And so this is ordinary QAOA for TSP. You start in equal superposition and you use X mixer. So this is ordinary QAOA, we call this XQAOA. But if you start in equal superposition of one-hot states for each register, meaning that for time t equals 0, you have this, for time t equals 1, you have this as the initial state. Now, using this initial state, you can avoid one of the constraints because you no longer have states like 1, 1, 0, and you don't need to check this. So starting in one-hot states, so this is QAOA plus, where quantum alternating operator onwards. You start in a different initial state, and you use XY mixer. Now we can avoid one of the constraints. And this is one more step. You start in equal superposition of all permutations. Now you don't need any constraints because now you make sure that in each register you have only valid one-hot states like 1, 0, 0 or 0, 1, 0, but plus you also make sure that at different time steps you are visiting different cities because those are permutations. By the way, by permutation, I don't mean I mean permutation of one-hot states. And you may say, okay, this is great. We don't have any constraints. But the problem with this one is that this creating equal superposition of all permutations, this is something costly. And this Grover mixer, which you need to use in case of starting with this permutation state, it is also costly. So that's the problem with this approach. And finally, we have QUBO. And here you have binary encoding, meaning that now each BT encodes city in binary, as I just have shown. But this results in higher order in a higher order problem. So those are the 4, I would say, popular QAOA versions we had, based on different representations of the problem. Now, what about FunQAOA? We don't need the explicit formulation of the problem, but what we will do is we will implement a program to represent our cost of the tool, and we will use another program to check if this BT forms a permutation. And we will use again binary encoding, but we will start in equal superposition of only valid cities. For instance, if we have 3 cities, we will start in equal superposition of 0, 0, 0, 1, and 1, 0. And for the mixer, we will again use Grover mixer. Now, I will explain how the program for each looks like. First, let's start with checking if some given numbers form a permutation. In this case, we have entities. So each B0, B1, remember, they're encoding the cities in binary. I act like if they're integers representing the cities. What we do is the following. The idea is to count occurrence of each city in modulo 2. you see we have those CIs, and those CIs, inside those CIs, we will count occurrence of each city. So this is just initialization. Then, as you can see for each t, so this means for each time step, for each variable b t, we will check if it is equal to I. This means if it is representing city I, and if this is the case, then we will increment the CI, but we will do this in modulo 2. Why modulo 2? Because actually it is enough to do this in modulo 2. And then at the end, we will check if all CIs are equal to 1. And if there is a CI which is not equal to 1, then we will set this flag to 1. And otherwise, we will set this flag to 0. So if at the end, all CIs are equal to 1, this means each city is visited exactly once, and we will return 0. And otherwise, we will return 1. So the corresponding quantum circuit will apply a penalization. So, okay, I wanted to show this circuit on the right-hand side here, but okay, let me show it right now. So you may wonder how we will check if BT is equal to I in a quantum circuit. In a quantum circuit, this suppose again we have 3 cities. This BT consists of 2 qubits, and I would like to check if it is equal to 2, let's say. And this can be done by applying bitwise modulo addition of K onto this quantum circuit, and then using some control blocks. So all those parts of this classical program can be efficiently implemented as a quantum circuit. And what about the cost of the root? For this, we will use a trick. We will switch from time to city representation. And this trick will help us in reducing number of required gates. So this is time to city representation, and this is what you have in QUBO formulation, meaning that you have binary variables of the form BTI, BT plus 1J, etc. And in this case, as you can see, you have a loop here going through all possible pairs of cities, and you have one more loop going through time points. In overall, you need to include your cost matrix n-cubed many times, and this results in n-cubed gates in the conventional QUBO approaches. But if one has city-to-city representation, meaning that if your binary variables are of this form, bij's, where this is equal to 1 if after I you are visiting j, then you already know that once you are in city I, you will visit some city, and there are n possibilities for that. And in this case, it is enough to incorporate the cost matrix n squared times, resulting in n squared gates. Because then if you check this picture, so this is saying after city 1, city 3 will be visited. And then for each city, you can check the remaining n cities if it is visited or not. And this results in n squared gates. How we employ this here? What we do is the following. First of all, we find out if, so we have here a flag variable. We check for all time points if, so we go through all possible cities, we go through all possible time points. And if at time t city I is visited, this flag is set to 1. And if this flag is set, we have this new variable called edge I, and this is set to BT plus 1. So edge I is recording the city visited after city I here. And once we do this, then we have another loop here. If edge I is equal to j, then this means after city I, city j is visited, and we incorporate the cost wij inside our cost. And this is how we compute cost of the root. And now, what about resources and optimality of the quantum circuit we obtain? First, let's check what is the best that can be achieved for TSP. In TSP, your solutions are all possible permutations, and there are n factorial of those. And to represent a permutation, you need n log n qubits. So to represent all permutations, you need n log n qubits. And this also determines your effective space, which is your sort space. So those are the lower bounds. You need at least that many qubits to represent a TSP problem. And also your sort space, logarithm of your sort space, this is how we define effective space, should be at least n log n. You need n square gates because the number of freedom is n squared. Your matrix, weight matrix, consists of n squared terms. And this is also true for parameterized gates. And for that, we can obtain the lower bound by dividing gates over qubits. This gives us n. And if you take the state of the art, I only didn't talk about MTZ-ILP, but this is another formulation obtained through integer linear programming. You can see that, like, on the left-hand side, we have the optimal, and on the right-hand side, you can see the other formulations. Some of them are optimal in some sense. For instance, for depth, XQAOA and XYQAOA, they're optimal. And for GM, I don't know, like effective space is optimal. But overall, none of them is optimal in all measures. And furthermore, you can see that none of them reaches n square gates. And now using this fine QA approach I just described, and using this, so this n-cubed gates was resulting from calculation of this cost, we were able to obtain n squared gates. And also, we were able to get near optimal cost measures of near optimal values for all the cost measures at the same time, simultaneously. So we have n log n qubits, we have n square gates. That is, so I mean, up to logarithmic factors, we get optimal results. And we also did some numerics for TSP problem, but it is limited to 6 cities. The first row is probability of measuring in the feasible space, and our fine QA is labeled by red. This is the one with Grover mixer, and you can see that, like, it reached probability 1 here. And also we have probability of measuring optimal solution and probability of energy scale in the feasible space. And here you can see almost, so we cannot conclude very strong things from here, but you can see that they all resulted in comparable patterns, I would say. But the thing is, our fine QA is using much less resources. We did not include GM-QAOA here because it was really the best when you put it in those pictures. But the problem is, it's really costly to prepare it. It has n-cubed gates, that is n squared, etc. So it's really costly to use GM-QAOA. And like, to conclude, we were also able to show near optimal circuits for max K-cut problem. We use this idea for set cover, and for integer linear programming, we show trade-off between number of qubits and gates. And also one can show a similar thing, a similar trade-off for graph isomorphism. So in general, you can employ this new way to implement QAA for any combinatorial optimization problem. And that's all. I will be happy to answer any questions.
Oh, wow, great. Thank you very much. You were perfectly on time. So we have plenty of time for questions as well. And there have actually been 2 questions in the chat from Shashti Kumar. And the first one you have partly answered. I'm going to read it because I think the recording doesn't show this in the, so it says, for constrained problems, does the optimal solution still lie in the ground state of the Hamiltonian? And then it says, how does the runtime of the QAOA scale with the size of the TSP or the number of constraints compared to classical? I think the second part was kind of addressed in a way?
So the first one, the constraints are, so the existence of constraints does not affect the ground state. So I can say this, and about the time. So if you are asking about the numerics, I don't know, like those are simulations of QAA, so they are not actual QAA runs. So we don't have like timing for them, so I cannot say something certain about that. But let me again check the chat if I'm missing something.
Yeah, but I think the table probably addresses what you can tell about the scaling that you have shown.
Oh, okay. I just open the chat. And we have a GitHub repo actually. I can share it in the chat. We have the paper on arXiv, like a preliminary version. And we also have a GitHub repo. I will share both the paper and the repository.
Yeah, great. Are there any more questions here? I can't see anything in the chat. I was going to have, did you yeah, okay. So did you check the resistance to noise?
Great
or
question. We had this in mind, but we did not do it yet. But we were also wondering how would it compare to conventional QAOA in terms of noise, because we have a really different way to implement it. But we didn't work on it.
Yeah, because that's kind of like going to be the question, right? If we're going for these NISQ applications, then one thing is that theoretically the algorithm performs better, but then the question is how does it perform on the real device? So I'm really curious how it works. I mean, it sounds really cool and a funky new algorithm. Cool. Okay, just okay, no, still no questions. We still have some time, so please go with questions. I will ask another one. So you mentioned, did you say that you applied it also to the max cut as well as the traveling salesman?
Max K cut, yes.
Yeah, max K cut, yes. And did you try any other application?
We had it. So right now we are actually working on applying it to factorization. Actually, this started as a QIntern project last year, and we are still working on it. So I mentioned set cover, and in general, you can apply it to any integer linear programming formulation, which encapsulates all combinatorial optimization problems. But like this factorization also is, I think, an interesting application.
Yeah, it sounds. And also just to mention QIntern. So there's going to be QIntern also this year. So stay tuned, and I'm sure Özlem will have another one, so you can apply also to it. No, you're not. No. But someone else would definitely have something. Okay, cool. So there's a question in the chat. David Liu, have you tried to optimize the circuit depth?
Actually, in the paper, we have results both for linear nearest neighbor architecture and general architecture. And we will be able to get like optimal depth in both cases. For linear nearest neighbor architecture, we used something called swap networks to like optimize the depth. So I will share the link and you can read it more there.
Okay, does that answer the question, David? Okay, I guess so. Right, anyone else? We still have 4 minutes. Okay, in the meantime, let me see if the next speaker is here, because I haven't seen the next speaker at the start. So Halil, Toprak, are you here? I actually don't see.
Cancelled because this is what Abu mentioned.
Oh, really? Okay. Well, I do know about that. And okay, in that case, Shauri Agramal, you will be the next one. We still have another 4 minutes until we start, so waiting for questions that we can answer. But I hope that Sharia will be here. Oh, okay, it's here. Excellent.
Hello.
Okay.
So should I wait 3 more minutes before I start presenting, just for more questions to pop up?
Yeah. Right. Okay. There's a question, right? Okay. So there's a question from in the chat, Rafael Vasquez, to Özlem, to the previous speaker. So is the QAOA a machine learning system?
I will not call it as a machine learning system, but it's what it is called as a variational quantum algorithm, meaning that you have some parameters to be optimized. This is also the case for instance, quantum machine learning algorithms. In that manner, they are similar. But QAOA itself is not a machine learning system. But it has some parameters which are optimized by some classical procedure. But other than that, it's like you have related quantum circuits. It's parameterized, and you try to optimize some expectation value.
Yeah, I hope that answers the question. Another one, Shashi Kumar, sorry. If I understand correctly, this Func QAOA requires arithmetic operation in the middle while the circuit is running. I'm not sure. I guess. Yes. I guess. Yeah. I guess the question. Maybe it was confusing that you were showing these classical programs on your talk, whereas they were actually quantum circuit implementations of all of the classical code in the actual algorithm.
But the question has a point that you may need quantum arithmetic in the middle of the circuit, because say you would like to add some numbers, then you would need quantum arithmetic to really add those numbers inside the quantum circuit. So the answer to the question is yes. Based on your problem, you may need some arithmetic operation. But for instance, the example I showed with permutation checking, there you can do this just by C-nuts, this counting modulo 2. It can be really easily done. You don't need complicated arithmetic. But as I said, it depends on it depends on the problem. If you would like to compute something which is more complicated, then yes, you may need